For those of you who don't know me, my name is Radhakrishnaiah Parachuru. I am with Georgia Institute of Technology in Atlanta. Originally, when I joined there as a faculty member in the School of Textile Engineering in 1988. I was teaching in the area of yarn manufacturing, fabric manufacturing, testing, all those areas, both theory and lab courses there. Then we were training textile engineers for the industry. A few years after I joined there, about 10 years after I joined there, the school became, it was originally School of Textile Engineering, so it became School of Textile and Fiber Engineering. Even after that conversion, we continued to teach textile manufacturing related courses there. After about 5, 6, 7 years, again the name of the school was changed, and this time it became Polymer Textile and Fiber Engineering School actually. So we started putting more emphasis on polymers and less emphasis on textiles after the conversion. So in that format, we continued for about 7 or 8 years. About 3 years back, our school was completely merged with the School of Materials Science and Engineering. So the former School of Textile Engineering now is a small division of fibers and polymers in the School of Materials Science and Engineering. So over the last 3 or 4 years, I've been more or less made to further textiles, and I've been teaching in the area of metals, polymers, and ceramics. So the manufacturing of metals, polymer, ceramic materials, and testing of those. We still have some labs. We still have a textile testing lab which I'm managing myself. We don't have any fabrication facilities in textiles anymore, so if we are doing some textile related, if any of our graduate students is doing textile related research, so we have to do the fabrication work outside of our campus actually. That is the state of the school as far as textiles is concerned right now. And actually, I've also been doing statistics related work for AATCC for the last 3 to 4 years. The reason for that is I have a master's degree in applied statistics, and actually that's the reason why I got involved as a statistician to work with the data generated by the different technical RA groups. That's what I've been doing for the last 3 to 4 years. For this presentation, originally I thought it is going to be a 30-minute presentation. So I prepared for a 30-minute presentation. When I came here this morning, I noticed that it is much bigger presentation, extending over more than an hour or so. Fortunately for me, I had enough material to put it together. So if you want, I can keep talking for 1.5 hours on this topic. So we have plenty of time.
Do we have, just before we start, do we have the roster going around for attendance? Here it is. Go ahead.
Oh, sure. So I'm going to take my own time and go very leisurely, and I'm going to talk to you about, make a presentation on 3 different topics. The first part will be on design of experiments. Again, the first part of presentation will be on design of experiments. The second part will be on analysis of variance, and the third part of my presentation is going to be on the data analysis report I have generated a few weeks back for RA75 on wicking properties. That is an example of a multivariate analysis which involves analysis of variance. So that is a real practical example that we are dealing with at AATCC. So the last presentation will be a real practical example of that applies to AATCC directly. So those are the three parts of my presentation. Again, going back to the parts 1 and 2 of my presentation, 1 on design of experiments and the 2 on analysis of variance. These are presentations I prepared a while ago to present to a group of nursing students meeting in Atlanta. They advised me to make the presentations completely non-technical in a way that nursing students can understand. So these 2 presentations have some medical application examples in them, and they are completely non-technical in nature. So I prepared those to present to a group of non-technical participants. So those 2 presentations don't have too much of technical content in them. Sorry. Maximize those.
I think go to slideshow.
Yeah, just go to slideshow.
Slideshow. Straight across the top there.
Slideshow.
Yeah.
Oh, sorry. I'm used to using icons here. Sorry. Experimental design, as you can see there, is defined as this is the definition for an experiment. An experiment is a scientific investigation in which observations are made and data are collected according to a set of well-defined criteria. That's something that we all know. Research design of a study spells out the basic strategies that researchers adopt to develop evidence that is accurate and interpretable. So the 2 terms are accurate and interpretable are important. The research design incorporates some of the most important decisions that the researchers make, particularly in quantitative studies. Quantitative studies, as opposed to qualitative studies, deal with actual numbers. The very first step in experimental design is defining the problem. Begin by asking a question about your topic. What is a good question for an experiment? For my particular experiment, what is the answer I'm seeking and what is the question I need to put in order to seek that answer? That is the very first step in an experimental design. Defining the problem. Begin by asking a question about your topic. What is a good question for an experiment? For my particular experiment, what is a good question? Good question is one that is testable with materials on hand. So once we know what question we are trying to answer through our experiment, the next question we need to ask is what is going to be my hypothesis for this experiment. You're best thinking about how the change you make might affect another factor. So the hypothesis is based on your understanding of what the change is going to be, that is arising due to the variable that you are introducing. All experimental designs have some basic characteristics or primary characteristics. A true experimental design is characterized by 3 parameters as listed there. The first one is manipulation, the second one is control, and the third one is randomization. Manipulation, there should be some text there. No way. Manipulation refers to the process by which the researcher manages the independent variable in order to study the effect on the dependent variable. So I'm talking about 2 different types of variables here. One is the independent variable, the other is the dependent variable. The dependent variable is the corresponds to the property that we are measuring. The independent variable corresponds to the variable that we are manipulating in order to see the effect of that variable on the dependent variable. Again, this is a medical example. I was having nurses in my mind when I made this example. Gentle massage is effective as a pain relief measure for elderly nursing home residents. The independent variable is gentle massage, which could be manipulated by giving some patients the massage intervention and withholding it for others. Then it is possible to compare the pain level in the two groups to see if differences in receipt of the intervention resulted in degree of pain levels. So we have an experimental variable here which is massaging, and that variable we are assigning only to one group of participants, and we are excluding that variable from another group of participants, and that group of participants we are calling as a control group. So in this type of study, you need to have a control group so that you can compare your actual results with the results achieved on the control group. Control. The experiment must be organized so that the extraneous factors are prevented from operating and confusing the outcome which is to be appraised. So there are many extraneous features that could affect our results, and our goal is to minimize the effect of those extraneous factors. The control over the experiment we are performing is obtained by manipulation, by randomization, and by careful preparation of the experimental protocols, and also by the use of comparison group or groups. Okay, here is an example to explain control. If a researcher wanted to supplement diet of the low birth baby with a particular nutrient for 2 weeks, the weight gain at the end of 2 weeks would tell us nothing about the treatment's effectiveness. So here is an example of a researcher trying to assess the effect of a nutrient on the growth of a baby. Suppose you are giving the nutrient for 2 weeks and you are measuring the weight of the baby after 2 weeks, and you notice a weight change of 1 kilogram. Is the weight change of 1 kilogram telling you anything about the nutrient? It's not telling you much. The answer will be no, because babies normally gain weight as they mature. As they age, they gain weight. Without the control group, that is a group that does not receive the nutritional supplements, It is impossible to separate the effects of maturation from those of treatment. So in this particular example, a control group is absolutely essential for your inference. Therefore, the term control group refers to a group of subjects whose performance on a dependent variable is used to evaluate the performance of the experimental group on the same dependent variable. So you have to start with a group that is not receiving the nutrient, and you have to have an identical group on the other side that receives the nutrient. You have to measure the weight gain after 2 weeks on the control group as well as the weight gain on the group that received the nutrient. And then you have to compare the two weight gains to see if the nutrient had a significant effect on the weight growth. Randomization this is also something that's very important in experiments. I want to give you a very practical example, taking a textile application. As a spinner, I will take a spinning example. Let us assume that we are trying to determine if the strength of yarn produced by 5 different spinning frames is significantly different. So we have 5 different spinning frames. Each of them is producing yarn. We want to know if any of those frames is producing yarn that is considerably weaker or considerably stronger than the average. So in the sample selection process, we need to follow random sample selection. So how do we achieve the random sample selection from 5 different frames? We have 400 spinning positions on frame 1, 400 on frame 2, 400 on frame 3, 400 on frame 4, and 400 on frame 5. Okay, I need to pick a random sample from frame 1, I need to pick a random sample from frame 2, and so on up to frame 5. So how do I go about selecting a random sample from each of those 4 or 5 spinning frames? What I can do in very simple terms, I can number the spinning positions on each frame. I can start with spinning frame number 1. I can call F1, 1, F1, 2, F1, 3, F1, 400. I can do the same thing for other frames too. F2, 1, F2, 3, F2, 4, up to F2, 400, and so on. So after numbering the spinning positions on all 5 frames, I can come back to the first frame. So for the first frame, I have 400 spindles. I have designated them as F11 to F400. So I put all those, I write all those designations on a small piece of paper and put them on a box. I shake all 400 of those pieces thoroughly, and I ask someone to pick one from the 400. He picks one, and I shake it again, ask him to pick one more. Picks one more, shake it again, ask him to pick one more. So if I want 12 samples from frame 1, I can do this, repeat this 12 times. So I can take 12 slips from the 400, and I can open it out and see the numbers there. So F20, F120, F150, F100. So if those are the numbers, I will go to the spinning frame, pick those spinning yarn packages. So what did I do in this process? Spinning frame 1 had 400 spinning positions. I gave exact same opportunity to each of those 400 spinning positions to be included in my sample of 12. So the exact same opportunity was given for all 400 spinning packages to be included in my small sample of 12. So that is what I call as a random sample. When you have, say, 10 million individuals in a population, you're only selecting only 20 out of those 10 million. you can randomly select those 20 samples from 10 million, and when you randomly select those 20 specimens from 10 million, those 20 specimens are a true representation of the 20 million population. Okay? That is how in all experiments we randomize them. So suppose in this example, also we are, for the healthcare example also, we are randomly selecting samples, but we have to assign those, half of those to the experimental group, half of those to the control group. So there again, in assigning those randomly picked samples to the experimental group and to the control group, you need to follow a random procedure. So you have, in this case, you have picked, let us assume again here that we have 20 subjects to be assigned, 20 people to be assigned, 10 of them to the experimental group, 10 of them to the control group. So what you can do is you can write all 20 names, put them in a box, shake all 20 names, and pick the first one for the random group, shake again, pick the second one for the control group, and you can repeat the process until you get 10 for the experimental group and 10 for the control group. So that is randomization essentially. The medical example here for random selection, the effectiveness of a contraceptive health education program for women. 2 groups of subjects were included. One group was given intervention, the other was not given intervention. The women in the sample are likely to differ in age, education, and attitude. This would affect the women's diligence in practicing contraception. Here, in addition to randomization, there is other parameter called similarity. So in a subjective study, when you're selecting people to be included in the study, you want the people, all of them participating in the study, to have somewhat similar characteristics of them. For example, if you're selecting women for studying the effectiveness of a contraceptive treatment, what you would do is you would select some of them for the experimental group, and you would select some of them for the control group. Those you select for the 2 groups should approximately be of the same age, should approximately have the same number of children, and you make sure that the groups, the people included both for the experimental group as well as for the control group have similarities. So going back I just now mentioned that in certain cases randomization is not enough. You need to also ensure similarity. Although randomization is a preferred scientific method for equalizing the groups, there is no guarantee that the group will in fact be equal. Therefore, we need a procedure to consciously control the characteristics of the subjects that are likely to affect the outcome, and this procedure is called matching. So matching is another parameter that we employ in experimental planning. If matching were used in the contraceptive education example, the researcher might ensure that if there was a married 38-year-old woman with six children in the experimental group, there will also be a 38-year-old woman with 6 children in the control group. That's how we ensure matching between 2 groups. I already talked about a dependent variable. This is a definition for independent variable and dependent variable. So dependent variable. The main guiding principle for any experimental design, max min con principle, it was defined by Kellinger in 1986, and this applies to all experimental design tasks. So you maximize the experimental variable. So whatever variable that you are manipulating, you try to maximize the effect of that. You choose the levels of that variable or the entire range. At the lower end, you start with the level of variable that has a minimal influence on the parameter that you are measuring. At the higher end, you use the level of variable that has the maximum influence on the dependent property. So you maximize the effect of experimental variable, minimize the error associated with all extraneous factors. And then the third parameter is control, exert control on extraneous parameters. So when you pay attention to these three, you have an experiment that you design appropriately to get the desired results. Major steps in selecting, major steps in experimental design: select a sample from the population by random sampling. Give you an example of random sampling. Assign the samples, once you select the sample, assign them again to different groups in a random order. Specify one subgroup as experimental group and the other as a control group. Before introducing the independent variable, observe and record all important characteristics of the two groups. So the control group as well as the experimental group, try to get all information about those two groups. Introduce the independent variable into the experimental group, but withhold it from the control group. So after you introduce the variable into the experimental group, you evaluate the effect of the variable using your experiment, pre-designed experiment. So the experiment gives you results, and you analyze those results to interpret the effect of the effect of the independent variable on the dependent variable. So this in short, this in brief is a summary of experimental design, what is involved in it. So I've described it in as non-technical terms as possible. So we have come to the point where we are generating experimental data by following an experimental design procedure. Now the next part is how you make use of that experimental data to generate interpretations that you need. So that part is that aspect is mostly done by analysis of variance procedure. So my next presentation is going to be on analysis of variance. Let me close this. ANOVA stands for analysis of variance. Analysis of variance deals with multivariate data analysis. Again, before I go further, I want to differentiate between multivariate analysis and analysis of data corresponding to just two variables. Okay, in a multivariate situation, you have several variables influencing one outcome. Let's go back to the example of yarn strength. If you're measuring the strength of a spun yarn, it is influenced by several parameters. The fiber type, the length of the fiber, the fineness of the fiber, the amount of twist you use in the yarn, the type of spinning system you employ, ring spinning, rotor spinning, adject spinning, etc. So those are all independent variables that influence the property of strength of the yarn. So when you are analyzing the strength of the yarn with respect to all the multiple independent parameters, you are dealing with a multivariate analysis. So this is an example of a multivariate analysis where a number of multiple variables, independent variables, influence the outcome of one dependent variable. What is an example of, say, a two-variable analysis of it? Suppose you're only concerned about how tall a child grows with respect to age. So you're only looking at age and height of the child. So there the dependency is between just two variables, one independent variable and one dependent variable. Dependent variable here is height, independent variable is the age. So you look at the relationship between those two variables. So that is a very simple phenomena in statistics, but in most cases, in textiles, we are dealing with a multivariate analysis where multiple variables influence the outcome of dependent variable. So in most cases, since we are dealing with multiple variables affecting the outcome of a single dependent variable, we need to use analysis of variance to interpret the data. As an example of basic ANOVA situation, again this is a medical example. Okay, when we have only two samples, so only two variables. Let's go back to the age versus height example. Let us assume that we are measuring the height of male babies and female babies with respect to their age. So first we choose a random sample of 20 children, 20 female children, and next we choose a random sample of 20 male children. We get their ages and we get their heights. So we calculate, we develop a database, age versus height for female babies. We develop a database of age versus height for the male babies. So we have on one side a two parameter variable, two parameter study. On the other side also we have a 2 parameter study, and both are small samples. So if we want to see if female babies are growing differently with respect to age from male babies, what we can do, we can apply a simple t-test. Okay? So we have only two variables, one dependent variable and one independent variable for both cases. So since there are only two variables involved, one dependent variable and one independent variable, we can apply a simple t-test to decide if the growth phenomena with respect to age of male babies is significantly different compared to the growth phenomena of female babies with respect to age. So a simple t-test will tell you that. So in our case, in most situations, we are not dealing with such simple examples. Again, I talked about categorical variables and quantitative variable. Male, female is a categorical variable. The height we are measuring by number is a quantitative variable here. So for ANOVA, I said we have multiple groups, not just males and females. We have other groups also. Actually, if we are talking about, say, a blue shade produced, the color fastness of a blue shade to sunlight produced by 6 different classes of dyes: direct dye, basic dye, acid dye, dispersed dye, reactive dye. Here we are not having just 2 groups. We are having 5 or 6 different groups. So when you're dealing with data that has multiple variables, a simple t-test is not going to do it. See if one is different from the other. So t-test will tell if you have only two variables, and will tell you whether one is significantly different from the other. When you have 5 or 6, more than 2, you need to apply analysis of variance. So when you apply analysis of variables on more than 2 variables, the question answered by the technique is this: do the quantitative variables depend on which group did you release it? Let us go back to the example of the 5 different classes of dyes and the shade produced by them. Okay? If one of them is producing a more durable permanency in the color shade, then analysis of variance will simply tell that there is the depth of shade represented by the 5 different classes is not the same. Okay? If all of them produce the same level of depth of shade, the analysis of variance will tell you that there is no difference in the depth of shade produced by the 5 different groups of dyes. So all it tells you is if one out of those 5 is giving you a different result. It doesn't tell you which one of those 5 is giving you a different result. It only tells you at least one out of those 5 is giving you a different result. Okay? So that is the inference you can get from analysis of variance. If you want to identify which one of those is giving a more durable result, then you have to go back and look at the individual data produced by the analysis of variance technique. It's a numerical example involving analysis of variance. We have 25 patients with blisters, and we are applying 3 treatments to cure the blisters. Treatment A, treatment B, and treatment 3 is a placebo. The dependent variable or the measurement variable involved here is the number of days until the blisters heal. Okay? We have 3 groups. Group A, Group B, and Group A receives treatment A, Group B receives treatment B, and Group P receives placebo treatment. Okay? So in Group A, one person is healing in 5 days, next person 6 days, so on. And the person in Group B, this is the number of days took by individuals for healing. In the placebo treatment, these are the number of days taken by the participants to heal. Are these differences significant? So for treatment A, the average number of days required to heal is 7.25. For treatment B, the average number of days required to heal is 8.825. For placebo, it's 10.11. So with these numbers, with these mean values for the days to cure, can we infer that treatment A or treatment B is better than the placebo treatment of that? So to answer that question statistically, you need to apply analysis of variance technique. You can look at the data even before you apply an analysis of variance technique to get the inference. You can map the data and look at the various variations shown by the data. That's one of those techniques is graphical investigation, side-by-side box plots, multiple histograms. This can tell you that this can reveal differences between the data, groups of data. So these are the parameters. Whether the differences in means we saw are significant or not will be determined by these three parameters. The difference, the extent of difference between the means, the standard deviations associated with each of those means, and the sample sizes associated with each of those mean values. Okay, this is an illustration of the box plot, comparison of the box plots for three groups. This is treatment A, box plot for treatment A, box plot for treatment B, box plot for placebo treatment. So this line represents the first quartile. The height of this rectangle represents interquartile range, the number of data points between first quartile and third quartile. This height represents the fourth quartile of it. So in other words, the height of this rectangle represents the mid 50% values for treatment A. The height of this rectangle represents mid 50% values for treatment B. The height of this rectangle represents the mid 50% values for treatment P. And this horizontal line represents the median value. This horizontal line again represents the median values. So you can see that the mean number of days required for cure here, or the median number of days required for cure here is lower compared to this. It's also lower compared to that. The extent of the mid 50% values range between 6 and 8.7 here, between 7 and 10 there, between 9 and 12 there. So from this plot you can see the extent of variation as well as the central tendency of the data, the mean, median values of the data. So this also gives you an initial interpretation about the result that you are searching. Okay? So what we are trying to test using ANOVA, are all three mean values the same, or at least if one of we are trying if one of those three mean values is different from the other one. So null hypothesis, we start with the hypothesis that all three mean values are the same, and if that is not correct from our analysis of variance procedure, we infer that the alternative hypothesis, true, null hypothesis is not true. Okay? There are certain assumptions data assumptions on the data that you make before you run an ANOVA exercise, and those assumptions are revealed here. Each group is approximately normal. The data of each group assumes a normal distribution. That's first assumption. You can check it by plotting frequency diagram of the data. The standard deviations of each group are approximately equal. So in other words, we have three groups in that example: Group A, Group B, and Group P. Group A has certain level of standard deviation and a mean. Group B has mean and standard deviation. Group C has a mean and standard deviation. One of the assumptions we are making in proceeding with analysis of variance procedure is that the standard deviation, the lowest standard deviation, when you compare the lowest standard deviation with the highest standard deviation, the highest standard deviation is not more than twice the lowest standard deviation. In other words, if Group A standard deviation is 2, Group B standard deviation is 2.2, Group C standard deviation is 3, then the lowest standard deviation is 2, the highest standard deviation is 3, the lowest standard deviation is less than 2 times the highest standard deviation, therefore you can proceed with the analysis of variance. Okay? Normality check you can check by these techniques. When you're measuring a parameter that corresponds to a human population, there is an underlying assumption that any dependent variable that you measure on human population is normally distributed. So for certain things, there is an inherent assumption behind that the data is normally distributed. So histograms you can plot to see if they follow a bell-shaped curve. If the histogram follows a bell-shaped curve, you know that the data is representing a normal distribution. The other techniques I'm not going to go with it. In our case, we have 8 data sets in one group, 8 data sets, 10 data sets in the third group. So this is a small data set. So normality assumption, checking for normality in a very small data set is not a practical way. And what you should do when you're dealing with very small samples, you should look at the standard deviations and make sure that the lowest standard deviation, the highest standard deviation is not more than twice the lowest standard deviation. Okay, let me go back to how ANOVA works. This is also a little more technical. Okay, this is where I want to start. Okay, this is even a smaller data set compared to the data set I used before. Group 1 has 3 values, Group 2 has 4 values, and Group 3 has 3 values. So we are running an ANOVA test on these 3 data sets corresponding to 3 groups, and I'm going to show to you how we run the test and how we interpret the results of it. So the variation within group 1 is called within group variation, the variation within group 2 is called within group 2 variation, the variation within group 3 is called within group 3 variations. So when you calculate the variation within each group, that variation is a within group variation. So when you calculate the variation across all groups, you call it as a between group variation. In general, between group variation will be higher than the within group variation because there are a lot more going on between groups as opposed to within group. So in an analysis of variance procedure, you are comparing between group variation with within group variation. So if you have a value for between group variation, a value for within group variation, you put the between group variation in the numerator and within group variation in the denominator, you take the ratio of those two. The ratio of those two will give you an F value or F statistic. So you'll get a number for F. If the number for F is low, that means if the number for F is say 1, F is calculated as the ratio of between group variation to within group variation. If between group variation is exactly same as within group variation, then between group variation divided by within group variation will be 1. That means between group variation is exactly same as within group variation. Therefore, there is no difference between the three groups. So that is the interpretation. So when you calculate the ratio of variances between group in the numerator and within group in the denominator, and that ratio is calculated as an F value, and that F value will help you to interpret if the groups are different from each other or not. Okay? So this is the statistics for those three groups. Group 1 has 3 variables, group 2 has 4, and group 3 has 3. When you add up the 3 values of group 3, you get 18. When you add up the 4 values of group 4, you get 23.8. When you add up the 3 values of group 3, you get 22.6. The average, 18 divided by 3, 23 divided by this, and 22.6 divided by 3. These are the average values for the 3 groups. And the variance is the square of standard deviation for those 3 groups. Okay, this is the variance between the groups. This is the variance between the group. The ratio of those two. You have to divide that variance by the degrees of freedom. When you divide the degrees of freedom by degrees of freedom, you get mean square, which is the parameter variation for both. So the degrees of freedom here is 7. The degrees. We have 3 groups. The rule to decide degrees of freedom is n minus 1. 3 minus 1 is 2. Okay? We have 10 independent values, and we have 3 groups. So the degrees of freedom here is 10 minus 3, which is 7. So that is the degrees of freedom for within group. And when you divide the total variance by the degrees of freedom, you get mean square for within group. And when you divide the total variance by degrees of freedom for within group, you will get mean square for within group, and the ratio of 2.563 divided by 0.250 is the F value, which is 10.2. So the between group variation is 10 times more than within group variation. So which leads you to infer that the group means are not the same. Okay. Again, F critical is the value obtained from statistical F tables looking at the 2 degrees of freedom. So if your F value is higher than the critical F critical value, you infer that the difference is significant at 95% confidence. Here is another step which goes in a little more detail as to how we obtain those numbers. These are the 10 independent values. 3 of them represent group 1, 4 of them represent group 3, and 3 of them represent group 3. The average for group 1 is 6, the average for group 2 is 5.95, the average for group 3 is 7.53. So when you subtract the overall mean, that is the mean of all values, is 6.44. So you subtract group mean from unusual values, you get these numbers. When you subtract unusual values from group mean, you get these values. When you subtract unusual values from overall mean, you get these values. Okay? So these are the difference between unusual values and group mean is given here. You square this because whether it is a positive deviation or a negative deviation, it is a deviation. So whenever you have plus and minus values for deviation, you have to square it and take this square value for that. Similarly, you subtract all these values from 6.44, you get the difference here, and you square it and get the square values here. You total all these squared values here, you total all these squared values here. So this is the mean square for within group. This is the mean square for within group. This divided by this will give you F value. That's how we calculated F value in the previous table. Okay. Again, I think that is what talks about what I have already discussed. So F is calculated as mean square between, as a ratio of mean square between to mean square within. And you can also plot these values here. Analysis of variance also gives you this plot. This is the mean value corresponding to group A. This is the mean value corresponding to this group B. So these means are for the previous data set I gave you, where you had 8 data values, 9 data values. So analysis of variance also plots the mean and spread, the mean and spread, the mean and spread for all 3 groups. So this also gives you the ability to compare the groups. The mean values are comparable, the variations are comparable for each group. Okay, that's in brief the analysis of variance procedure we use after we generate data through experimental design. We use analysis of variance to interpret the data. So I'm going to stop it here. I'm not going to go through the AATCC example because we are already more than an hour. I think we've gone through it. Okay. Any questions for me? If you want me, if you want me to go through that example, I can go through. But I think it's better to stop it here. Okay.
Thank you very much. Thank you.
Thank you.